Hi everybody, I'm Mr. Huntz, and I'm Mr. Huntz standing a certain distance away from the wall. In fact, I'll tell you exactly how far I am standing away from the wall. I am standing 153 centimeters away from the wall. 153. There we go. It's a number, right? You know that it's a number. In math, if we just have a single number, we call that a constant. It's going to be 153. It's always 153. Maybe, however, we're not sure how far I am away from the wall. In fact, sometimes I move around in front of the wall. Then we have to come up with something that represents how far away I am from the wall, but we're not really sure what it is, right? You know what to do then. You would say, well, we're going to make that a variable. And we might, in this case, call our variable d. And of course, you can see just by putting those two definitions side by side, constant and variable. Oh, they're opposites, right? Constant, always the same, constant. Variable, changing, right? So when in algebra, in math, we put in a variable, we are putting in a representation of an amount. Okay, this is a good definition. A representation of an amount that is unknown or changing, I suppose. Now, of course, there's a lot of things that we could do with this variable d, right? We would have defined it, and we would have, of course, done a let statement, say let d be the distance from the wall, right? In centimeters. I'm going to be very picky about including units when you do a let statement or declaring your variable. So if d is the distance from the wall, we could do a lot of stuff with that. We could say, well, maybe I don't want to talk about just the distance from the wall, but I could talk about twice the distance from the wall, right? Or half the distance from the wall. In that case, I'd be talking about 2d, twice the distance from the wall, or half the distance from the wall, half of d, half times d, or another simpler way of writing half d is d over 2. Same thing. We might say, 3 centimeters or 10 centimeters past where I'm standing, right? D plus 10, right? 10 centimeters farther away from the wall, or maybe even, 50 centimeters closer to the wall, right? Back 50 centimeters. And we would say, well, that's the distance minus 50, right? D minus 50. We could even get pretty fancy and say, well, I'm going to make a square out of the distance from the wall, and that would be the area in that square would be d squared. Now, as soon as I've included my variable in any kind of addition or subtraction, like saying d plus 30 to say 30 more than d, or d minus 50 to say 50 less than the distance to the wall, then I am using an expression. Now, I could even get so fancy as to include a second variable into my expression. I could say that the distance that I'm standing away from the other wall would be e. And now the distance, I could say that the distance between the two walls then would be e. And this would still be an expression. So any addition or subtraction that involves variables, right? Any of these, anything a little bit more complicated, right? Like if I was to include some other aspects like 2d plus 3e, or 4d squared plus 3de, right? We're getting really complicated, and it might not be hard to actually say what these mean in this situation, but anytime I have any combination of variables that are being added together, right? Any of these are all expressions, and expressions are made up of terms being added together, right? Here's a term, here's a term, here's a term, here's a term. How do you know where one term ends and the next one begins? Well, they're always separated by either a plus or a minus. So 5x squared is a term, 5xy is a term, 6y squared is a term. In these terms, there are variables, so these expressions could have any value once you started putting in numbers for the variables, right? If we said, well, I want d to be 20 and e to be 50, well, then all of a sudden these things are going to have real values. But for right now, we don't know what d and e is. We don't know what x is. We don't know what y is. So this thing could turn out to be anything. But we do know that these are all expressions This one's made of 2 terms, this one's made of 2 terms, this one's made of 3 terms. And these terms can have variables in them, right? They can have coefficients in them. I could even write an expression that included a constant, right? D plus 30. This has 2 terms, right? D is a term, this very simple term. 30 is a very simple term. In fact, it's a term called a constant. So what's the thing about expressions? Well, besides the fact that they are always have a couple terms, at least 2 terms that are added or subtracted together, the thing about expressions is that they still have no fixed amount, right? Even if I knew, for example, that this distance between me and the wall on the left was 30, I could still come up with an expression for the distance between the 2 walls. It would be d plus 30. I still don't know how far the walls are apart. So I would say expressions can represent any amount. If I were to know even less information and just know I was, d away from this wall and call the distance I am away from that wall, define that as e, then the distance between the 2 walls would in this case be d plus e. It would have 2 different variables in it, and but I still wouldn't know a definite amount. It could be any amount. D plus e could be any amount. Now, occasionally, I will be given some numbers to put in to my variables, to substitute. For example, I might see the instruction evaluate for d equals 100 and e equals 75. And in that case, I would do exactly that. I would evaluate, I would figure out what the value is, and I would substitute in correctly using brackets, 100 for d and 75 for e, and then I could figure out that this, of course, equals 175. The distance between the 2 walls now has been given a definite amount because my variables are no longer variables. I put in constants for them. So I would just add the little note that expressions can be any amount, but they can be evaluated once the variables are known. But because I could put in anything for d and anything for e, by definition, expressions can be anything. After working with expressions, it's nice to move on to equations, because equations have something that expressions just don't have. They have solutions. No more just wondering what could be or wandering around in the infinite possible things that they could be. We get some definite answers, because an equation will include an expression. For example, we might have that the distance between the wall is still d plus 30, but because it's an equation, we will also find out that the 2 things actually make something definite. For example, if d plus 30 equals 120, you know how to solve an equation, right? You know how to solve that equation. You subtract the same thing from both sides, just rearrange, and we find out that, oh, here's a little very, very simple equation that tells us exactly what d is. D cannot be just anything anymore. We've actually worked it out that d must be 90 according to the equation that we've been given. Now, one thing I can promise you will happen over and over again in this course is I will ask you, well, how many solutions does this thing have, right? If we go back to expressions, how many expressions or how many things can an expression represent? Well, an infinite number, right? Once we say that d is the distance from the wall, I could be any distance from the wall. If I stood on the other side of it, I could even be, right, a negative distance from the wall. I could be anything. In this case, if I take this example that we just looked at, where we defined the distance plus 30 being equal to 120, we came up with one and only one solution, right? But throughout this course, I'm going to keep asking you, well, how many solutions can we have? Is there an infinite number of solutions? In this case, no, there's only one. I want you to consider the example that just popped up here. 2x squared minus 3 equals 15. Now, if I asked you to solve that, you would know what to do. Well, I need all the variables on one side. I'm going to need to move, right, 3 to the other side by adding 3 to both sides. So 2x squared equals 18. I'm going to have to divide both sides by 2. And I'll get that x squared equals 9. And we all know that if x squared equals 9, then Technically what we need to do is we need to square root both sides, but we know that x equals 3, and there is the solution. Only I want you to consider that x equals 3 isn't the only solution, right? If we just look at these last two steps here, x squared equals 9, let me ask you this. Could x also be perhaps negative 3? When you square negative 3, and if you do it carefully, right? Negative 3 squared. If you square the negative 3, including the negative, you get positive 9. So this is actually, the example I've just given you here is an example of an equation that has two solutions. X equals 3 and x equals negative 3. Okay, and we're going to see examples of things that have more than one possibility. Okay, when we're dealing with expressions, we're dealing with things that have infinite possibilities. Equation, we often whittle them down to one solution, but sometimes there's more than one solution, and sometimes we'll get an equation where there's no solution. But more on that later. The nice thing about equations is that often they are defined down to one thing. So then, what is a function? We've talked about expressions, we've talked about equations. A function is what happens when we make an equation that has more than one variable in it. Right? If we said, well, the distance between the walls we're going to call d plus e. Now again, that's just an expression, could be anything. But if we make an equation out of this expression that has two variables in it, we say, well, we know that I'm standing somewhere between these two walls, and I know that the distance has to add up to 120. Now we find ourselves in a situation that still has an infinite number of possibilities, but now I'm not talking about an infinite number of possible things that this can be, but there's actually an infinite number of possible solutions, right? Equations have solutions. But in this case, it's not enough to say that the solution might be that d equals, 70. We would have to say, well, the solution that would make this true would be that d would equal 70, and then e would have to equal 50. Right? That's one possible solution, but it's not the only possible solution. And right, we could say, well, if d is 71, then another possible solution, or the other half to this other possible solution, would be that e would have to be 49. Right? And we actually end up with a whole pattern of solutions. And if you're willing to see it, then what you see is that d and e have a relationship. And I want, anytime when I say what is a function, I want you first to say it's a relationship, right? When d gets bigger, e gets smaller. When e gets smaller, d gets bigger. They affect each other. There's a relationship here, and the relationship is defined by this equation. And there's lots of different ways to demonstrate this relationship, right? You could first and foremost talk about the equation, and that could show you the relationship. You could draw the picture, right? Last year you showed relationships by graphing, right? Or by a table of values to say, well, when d is this, e is this. So I want you to always keep in mind that a function has an infinite number of possible solutions, but it is first and foremost a relationship between two or more different variables. So, to summarize, an expression will have variables in it, maybe one, maybe more. In this course, you will be asked to do things like simplify your expression or factor an expression, but ultimately, we never find out what that expression actually represents, a definite amount. Unless you are given numbers with which to evaluate it. Now, equations, at least the ones that we're going to be dealing with, will often have one variable. You will be asked to solve your equation, to find a solution, right? Find out what that variable amount actually is. And often there will be one solution, but there may be more, sometimes less. Now, in order for a function to be a function, it has to have at least two variables. The ones we're going to look at will have two variables. A function is an equation that defines how the two variables have a relationship. And examining that relationship usually yields solutions, actually an infinite number of solutions. Each solution which is made up of definitions of variables, right? Where what you know what one variable has to be if the other variable is something. And you'll be asked to do a whole bunch of things with functions. One common thing you'll be asked to do is to graph the function. And there you have it. So expressions, equations, and functions, kind of the basics on which most of this course and many of your future math courses will be based on. So hope you understood this. Hope you grasped the differences between them and how they relate to each other. Because we will be building on this throughout this course and throughout your math career here in high school.